Okay. Again, thank you to be here for the lecture today evening. Let me restart from the slide in which we stopped. Do you remember I told you about, again, this example is an engineering example, but as I told you before starting here the official lecture, you can apply Kalman filter everywhere. We will see this general application using very abstract examples too. But I will tell you, it could be also today. You remember I told you I promised that I would. The idea was to show you also, another example, from, for instance, from the economic field. Do you remember last time I introduced the discretization? Then I also tried to sketch the difference between forward Euler and backward Euler. Do you remember I draw is the difference? Forward, backward is not at this moment extremely relevant. It could be that today I will introduce the economic field and then we will come back again on this topic of the discretization. Of course, different discretizations, I would like to say, make different Kalman filters. This to keep in mind, even though at this moment it's a little bit difficult for you to follow me, but the discretizations realize different model. We can see here that in accordance with the forward Euler, we have the model which consists of these two equations. We depend of Ts, we depends of the parameters, but in particular, we can see that with this discretization, we have on the left part, let me say the present as the function of the past in both equations, or you can say the future as the function of the present, but with different discretization, not only the structure is different, also some very important characteristics as stability, dynamics. About the stability, I didn't tell you much. I hope during the semester to try to tell you something more. But of course, the course is it's intuitive in this sense. The content is not extremely mathematical, even though you can see at this moment I show you just mathematics. But believe me, I try to simplify it a lot. In this sense, simplify the course. In other senses, extremely difficult because it's not so precise what I am telling you. But in accordance with your background, I have to mix a little bit. I would like to say in different discretization, it could be that it's not so easy to separate presence on the left or future, if you like, past on the right or present, depends, if you like, because some discretization we say are implicit discretization. They have particular characteristics but realize a different model in the sense. You remember I told you about the possibility to build this information here, or to reformulate this information here in form of matrix and vector. And you remember I told you, please pay attention, everything depends on Ts. Everything depends on Ts. Ts is everywhere because we realize a discretization starts from a continuous system. And in particular, if Ts is very small, you remember this concept here, it seems that I approximate the derivative of a signal very well. You remember also in gymnasium, no? If the distance, I don't know if you remember the scheme, if the distance is very small, if you want, I can redo this between two samples. It seems to be that statically I approximate very well the system, the signal, but not the system, because if Ts is very small, look, close to zero, we have here an identity matrix, 1, 0, 0, 1. which states a not observable system. Do you remember the concept of the observability? Yeah, the observability is based on the connections between the states. Now, if the matrix is an identity matrix, we don't have connections. Or if the matrix tends to an identity matrix, we don't have connection between the current and omega, or x1 and x2. Look here, probably we can see better here. If t is equal 0, this is 0, this is 0, we have ik equal ik minus 1. I destroy the dynamics. I don't see difference between present and past. This means I cannot predict, I cannot describe what happens. This means in Gymnasium we learned that we can approximate very well in a signal if the distance of the sample is very small. Should I clarify with it? Okay, because it could be that is far away in the time. No? I try to explain this concept here because it's also important. Because you remember one of the key point is the choice of TS. Now in this course I cannot go in depth really in the choice of TS, but I would like to give you at least some indications. Of course, for engineers, in which TS really can be, we can choose TS in the microcontroller. It's quite clear that the meaning what I am saying. Look at this. I try to repeat a little bit what I told you last time. You remember this picture here? Something like that I did. Do you remember this concept? I did, last time. No? This distance here, which is equal this distance, we consider TS constant, could be also variable, but this is also a more advanced Kalman filter, but could be also variable. Now, if you remember what I told you last time, and if you remember what you learned in Gymnasium, I approximate the continuous signal with a stepwise continuous function. This means it's just step continuous, but we have a discontinuity, and I approximate the continuous line with this. Last time I told you the difference if I consider a backward Euler. I will come back, but let me focus on the TS. It's clear if TS is smaller, I have a better representation. Look, with another color. I take the initial value and I take half. I don't know if we can see that the red color, the red approximation is better. I don't know if it's visible. No? Yeah, statically, it's valid. This means, of course, I can represent better the signal. If TS is very close to 0, do you remember the concept of the derivative, not the limit, excuse me. But dynamically, let me come back on the lecture, let me go ahead. It's just a repetition of what I told you last time. Dynamically, I destroyed the system. This means TS cannot be very small. What is the meaning of very? We have to discuss, but a little bit too complex. Keep in mind that, of course, cannot be infinitely small, cannot be small. How small is a big problem. But also cannot be very large, because we have seen that statically I have some problems. This means we have an optimal TS. This is a very interesting problem also for bachelor thesis, no? To optimize in the Kalman filter the choice of TS. Of course, this is more for engineer, because as I told you in economics, very often TS is given. If you sign a contract, I show you later this, in the bank, that you have interest each 3 months. the step is 3 months, because until 3 months does not change in accordance with the law of the bank, the money. Of course, if you withdraw or put money, will change, but basically the dynamics will update it again after 3 months. I will show you a little bit what I intend, because it seems to be not exactly correct, but I have to show you the equation. Okay, here, last time I told you that I can also apply the discretization using directly the matrices. You don't have to learn this, but just to show you that we have the possibility to apply when we have the matrices, the continuous matrices, which is here, or are here, A, B, C, and D. D is equal to 0 in our course. Without doing these calculations by hand, we can obtain this expression using this general. I don't have time to demonstrate this, but it's not so difficult. Using this general discretization, but we don't have to learn. But because MATLAB does directly with the command. This means when understood what MATLAB does, we don't have to learn this. In a linear case, we will come back on this problem of the discretization. It's a shame we have to do by hand. Of course, we have also programs that help us. Nevertheless, MATLAB is a good tool to also do discretization in each kind of, let me say, format. Last time we concluded here, because here is the first slide related to the Kalman filter. Let me reconsider here. Also, in accordance, I think it's already. Okay, it's not so nice, but could be better if you see me. Yeah. This is the first slide for the introduction of the real Kalman filter. You remember the motivation of the Kalman filter. I simulated using the Lundberger observer some critical situations. Noise, error in the model, few things basically. Error in the initial condition, 3 things if you like. But error in the initial conditions was not a problem for Lundberger observer. Absolutely no problems. The problem appeared in accordance with this Lundberger observer. If, of course, if you have more advancements in Lundberger observer, we can solve also the problem of noise in the measurements. We can solve also the problem of which we don't know in the model. But I would like to say that the Kalman filter is more advanced Lundberger observer, even though it's not exactly what I say, because we will see now the structure is a little bit different. But if you want, you can say in some books you can find also this sentence here, even though the structure is not. We have some similarity, but it's a little bit different. Look at these tables here, 2 tables. First of all, look at the notation. In Kalman notation, in particular, in this paper which I signalized, you remember I signalized this. Let me come back because it's important. Because at the end of this lecture, you can almost try to read this paper here, which you can download. You can start to understand. I am sure about that, and we will understand better, also me, during the semester. But now should be important slowly to download this, because in the summary, it's the basic summary. It's the basic summary of the basic knowledge of Kalman filter, and then we are also in a variation of Kalman filter, the basic knowledge of extended Kalman filter. Yeah, we can see A in this notation is AK. This means we assume that the system is already discretized. B is equal BK. And look, do you remember last time I told you the unique difference between what I told you until now in this table here is just this row here with 3 columns, in which I say that we have a variable, we can see here, which is in a vector, we can see here because the dimension is n with n component, is a vector with n component, exactly as xk. The name is system noise. I insist on the name because in the name we have the meaning of the thing. Also in how possible to say in cultural scientist, in culture, in humanity, the words, in the words we have the meaning of the thing which we want to. Somehow the name defines somehow the thing. Look at this. Here is a vector similar to xk, because similar in the sense the similarity consists just in the dimension. But of course, we have a big difference. We can see the word noise. Noise means, in the sense we will see in this Kalman filter, which I present in this course, is a random variable. Random, you understand what this is? Gaussian variables from gymnasium, a little bit change randomly. But is characterized, we will see in our Kalman filter, by a Gaussian distribution. If you don't know exactly a Gaussian distribution, take just the words. To remember variance, mean value, expected value. I don't tell you much about that now. The meaning is, nevertheless, the meaning is that I can associate to the system, therefore system noise, and in particular to the states or the states vector, an uncertainty. Something we change over time randomly as a Gaussian variable, the sense with the distribution which reflect the Gaussian distribution. Of course, this is an assumption. We have also Kalman filters with different distributions, but in this course we will do that. Which is most important, because if you remember in statistics, all other distributions tends to the Gaussian distribution, but in general, in the most natural distribution, in the natural phenomenon, or the phenomena, the Gaussian distribution dominate the behavior. But just to understand why in this course we are speaking about just this noise, all noise which we are introducing as in a Gaussian, within a Gaussian distribution. If it's not as clear, we cannot obtain the same results or the expected results, which I will present it. But anyway, we have also more advanced variation of Kalman filter once you understand. Once you understood this Kalman filter, you can go ahead with different variations. Look at this. Here it's quite similar what I told you for in case of Lundberger. Instead of H we had C. Instead of H we had C. Instead of Z we had Y, I think, YK. The difference is this row here, which we have again as noise, again a Gaussian noise. The name is measurement noise. This means this noise is connected with the measurements, but of course could be also connected within the model, which can be seen in output. This is a little bit an advancement. I don't know if I have time in this course to tell you about that, because a little bit advanced, I hope. Some advancements in a similar course I consider in master. But of course, with bachelor thesis, this aspect could be done also through projects if you want. This means in both tables, the new elements which we have is these two noises. And the system noise, a little bit abstract in the sense what I don't know of the system is characterized, is modeled, I would like to say, within a Gaussian variable. Here is more concrete, because if you think about the measurements, error in the measurements is more clear what I intend. instead of measuring 1 volt, because 1 volt is the true, but no, just God knows the true. The instruments measure 1,1. One's 1,1, the other, after the second measurement, they measure 0,9. We can see a little bit the difference between. Or in general, error in the data. I told you about the COVID and so on. Okay, let me start roughly to introduce the Kalman filter. We can see here in this slide, the message is we have basically in the Kalman filter, the picture is not really a good picture, but I try to explain what I intend. It could be also improved. The Kalman filter basic consists, please pay attention, internally, within a sample time, we can see at the end, of 2 steps, prediction step and correction step. Fix this idea. Prediction step and correction step. This is also something new. Therefore, I told you something new respect to if you think about the Lundberger observer. Therefore, I told you we can say as an advancement, but we have big differences in between. But anyway, we will see also some analogies later. Again, we have 2 steps inside or within a sample time. This means internally. One is the prediction step, or in some books you can find a priori approximation. And the second one, or the other step, is in a correction step. In some books you can find a posteriori correction, or sometimes a posteriori approximation, as you want, but correction I like more correction. Look, we have here another important word, optimal approximation of the state in the context of Kalman filter. We can see that we can approximate many things, not only the states. We will see that this optimal, nevertheless, under some conditions, this Gaussian and also other conditions. We can see the interconnection between the prediction and the correction step. And let me go in depth now. Okay, now this is a little bit more difficult. It's a little bit more difficult here. But I try to simplify. The equation 1 is no somehow. Because the equation 1, or a part of equation 1, is what I already told you, at least if you don't consider W, this equation 1 is known because it's exactly what I told you here. Remember last week? Yeah, it's my stupid motor. Which at the end I have an expression which can be written, can be read x hat because it's the model. If you don't like x from of k equals ak, which multiply x of k minus 1 plus b of k. K in Kalman filter we omit because it's clear that is discrete. We don't consider continuous form of Kalman filter. Multiply u of k minus 1. And also this equation here, we will see later, which is basically the discretization of the output equation, we have already seen. But let me consider again this expression here, which can be seen in quite general form here. Is exactly what I told you if you consider A equal AK and B equal BK. I didn't put hat here for an important reason, which I will clarify now. Because I put here hat characterizes the observer. Remember, in the first lecture, Lundberger observer were characterized by hat. An approximation, characterized an approximation. Here it seems to be that this equation 1 is the true. Is the true of Kalman filter. In the sense, what I know of the system is characterized until here, without considering this noise. What I don't know is characterized by W. for each equation, excuse me, all equations are characterized by an uncertainties, which I put in W vector. Basically, what say equation number one? Says that the true is what I know plus what I don't know. Isn't it tautology? You know the word tautology? Yeah, you should know because you're cultural. Tautology. There is an interesting sentence in the rail station of Ulsen. Did you visit the rail station of Ulsen? There is, how possible to say in English, running, let me say, sentence would say, this is not tautology, this is not tautology, this is not tautology. It's running on the, if you look at the table of the train, this is not tautology. Tautology is a repetition. If I say A equals A equals A is not a tautology. I repeat the same concept. What the reality is, do you define tautology? It's strange that I am not in German. I know very few words in German, but tautology is an important word. I am saying now, the reality is what I know plus what I don't know. It's quite similar to say A equals A because I say something which the reality in this form here, the reality is xk. Huh? How the motor runs in terms of current and velocity is equals what I know of the motor plus what I don't know of the motor. It's clear that it's more or less it's the same if I say A equals A. Good. I can believe that A equals A. I mean, it's something which belongs to our a priori knowledge. A priori is clear what I intend, no? A priori knowledge. A equals A, we don't need to explain. It's now tautology. Sometimes tautology is used in a tautological question. You know that? The tautological question is a question in which the answer is included in the question itself. Do you know what is the yellow color of the sun? This is now a tautological question because I already answered the question. A equal A, and I mean we can extend a little bit of the word the tautological. It's a repetition. Huh? In the question, I already introduced the answer. No? I repeated it. Oh, yeah. Again, coming back to Kalman filter, the first equation says that the reality or the true is what I know plus what I don't know. Good. I can believe that this sentence is correct. But in any case, the importance of the question of the equation here is the introduction of this variable here. We will see the characteristic of this variable here. The second equation is the equation of the output. In this case, we can consider or in this course almost just measurements, but of course can be also included in the second equation a part of the model. In more advanced Kalman filter, we can use this, in which basically without this V is exactly what we have seen until now. Instead of H, we had C. Instead of Z, we had Y. No? I changed nomenclature because we have two different nomenclatures, one for Lundberger in the literature, one for Kalman filter. Again, here I put this measurement noise because the measurements are not correct. That the measurements don't tell the truth. We don't have the truth, basically. We have always something affected by errors. A little bit more difficult if equation to include also a part of the model. I don't know if I have a time on this course to tell you, but we can consider the project, we can consider the bachelor. Look at the characteristic of this W and V. We can see that the density of the probability of W is the normal distribution with mean value, expected value 0, and variance Q. Really, we cannot speak about the variance because we have more than one variable. This means we speak about covariance. We can see here the word process noise covariance matrix. The reason is the variance is clear what I intend. If I have just one variable, and a Gaussian distribution can be characterized by the mean value or expected value and its variance. If I have more than one variable, the situation is more complex because we have the connection between. In this case, we speak about covariance. I tell you a little bit in the next step, but very shortly because mathematically a little bit complicated. The same consideration can be done for the variable V, the measurement noise, which again is characterized by the normal probability distribution. Again, expected value 0, and covariance if I have more than one measurement, or variance if I have just one measurement, R. Again, look at this sentences, two sentences at the end of the slide. I already told you the nature of the two variables, random, yeah. But we are assuming that they are independent, white. I told you a little bit about white, and with normal probability distribution. Normal, I already told you, Gaussian, which is characterized as expected value, variance or the covariance, because now we try to understand what I intend with covariance a little bit better. White, this means that for all spectrum, this is a little bit difficult to understand for not engineers, for all frequency of the signals, we have the same probability distribution in this sense. And independent, this means that W and V, they are not dependent each other. Let me look if I forgot to say something. White, I don't know if you remember, the engineers remember, this means the spectrum is in a constant. It's a little bit more difficult for not engineer. Forget this aspect here. Think that we have some hypothesis. We have some hypothesis. If you think about that, I don't know if you remember the mean value. I don't want to insist now the difference between mean value and expected value. Let me say is the same at this moment. This is a little bit the definition of the covariance matrix. Forget also this mathematical aspect, but try to think that we have a connection between the variables. The reason is the system must be observable. Remember, this means we have a connection. This means the covariance measured in a statistical way how the system is connected in a statistical way. If I change the current, if the error of the current, or if I change the current, I don't know, 1 ampere, what is the influence in the velocity? This means it's not enough in a variable because we have two variables which is connected to each other. This means we have a matrix 2 times 2 which try to describe the statistical connections between the two variables. But in the diagonal, we have the variance of the current and we have the variance of the velocity. But of course, we have also these two components which measured the interconnection between. At this moment, don't learn this, just the idea. It's not enough as an invariant because we have two variables. They are connected because otherwise I cannot implement an observer. We want to implement an observer in the form of Kalman filter. And this means I need something more than one parameter. I need a matrix with 4 parameters because we need the variance of both variables and the interconnection between sigma 1, 2 and sigma 2, 1. They are the elements of the covariance matrix which measure the interconnection between, statistical interconnection between these two variables. Takes just the feeling. Forget the mathematics. This is the goal of the course. Now we will see how we can apply this. It is easier than to explain. Let me start with the 5 equations. The first equation is the equation A, or equation number 1, which must be applied with if you want to implement the Kalman filter. Let me start from this equation at the end of the slide. We can see here that it seems that the first equation consists of the a priori knowledge which we have of the system. Look, we have the matrix A with the parameters which we know, with Ts which we know. We have B with the parameters which we know, with Ts which we know. Basically, this expression here formally seems to be very exactly what I told you until now. Also, when we starting building a model of the system. But please pay attention. Het is no, it is this observer. No, characterize the observer. Makes sense because our true, or the true of Kalman, is this equation here. This is the true, which is what I know plus what I don't know. We can believe me. The true is what I know plus what I don't know. What I know plus the error. What I don't know could be considered also an error. I don't know, it's a little bit philosophical, but we can understand. Here, if I cancel this, I have a hat, I have here a hat. Because it's an approximation, it's an observation, it's an estimation. But look, here we have something more than hat. We have minus. This is interesting. And here I don't have minus. Please pay attention. In math, in this sense, is, in my opinion, didactically math is very important. Everything means something important. Otherwise, I don't put. Why I put minus? I didn't put here. If I put here minus, okay, I change the variable. But here, we have another meaning. And anyway, I come back to this in 1 second. Let me say this equation here, the first equation of the Kalman filter. The name is a priori estimation of the state. Or let me say a priori estimation. Boom. In this case of the state is correct, but more in general. Why now I put here minus? Because as I told you at the beginning, we can speak about 2 steps. A priori, let me say step, a posteriori step. We have this all characterized approximation, correction. Anyway, a priori step, a posteriori step. In this sense, we can see that here we have 2 possible definitions of errors. We can see an a priori error estimation and a posteriori error estimation. Look, the a priori error estimation is quite clear because it's what I am considering as a true minus this x k hat minus, in which it seems to be important now, because if you look at the a posteriori error, everything is calculated without minus. This means this element here it's something which should come from the second step. I mean, minus is related to the first step, or the a priori error. Do you remember? First step reflect the a priori. Second step reflect the a posteriori. No? A priori approximation, a posteriori correction. Forget the adjective again. A priori, a posteriori quickly. No? This means is also here the concept of an recursivity of the algorithm. I mean, the a priori and the a posteriori, they are connected through this equation here. To remember the sketch, this loop. We will see a little bit better in a few minutes. I need a little bit time, but it's not so difficult to see that the previous step come back for the next a priori approximation. We will come back on this in also with MATLAB. It's easier to implement than to explain. But this scheme here, somehow you can intuitively understand that it's already in this equation here. Because the a posteriori correction, second step, is coming back to estimate the new, k is the new, this is the past, you remember? K is the present, k minus 1 is the past. But they belong to different procedure, to different step. Because we have two different errors. We will come back on the a posteriori in a few minutes. A priori is xk, which I already introduced here, the true, because the true is what I know, plus what I don't know. Xk hat minus is this expression here, in which is not clear yet what is x hat without minus, but in any case, is something which came from the previous step, because it's k minus 1. I mean, this equation here is totally different with this equation here. Because here, we don't have minus. The recursivity is not there. Here's just a mod. I come back 1 second on this again. I will repeat always the same concept in order to, I hope to understand better. Here we have the true minus the a posteriori correction of the variable which I have at the second step. But xk hat without minus is not clear. Really, it's also not clear xk hat minus, because it's not clear this. It's not clear xk minus 1 hat. But let me complete the Kalman filter. Yeah, this is just a repetition. I already told you this is the true. What is xk? Please pay attention. Equation B, second equation. We are going on. The second equation is very easy but boring to be demonstrated. I will not do it. I will just sketch the demonstration. But it's based, the equation B, on this consideration which I am doing here. Basically, I will calculate the a priori estimation error covariance. I don't know if you remember in statistics, the covariance is the expected value of this, of the variance. Let me say that because the covariance matrix is a little bit more complex to be calculated. I don't know if you remember the covariance, which basically is the expected value of the error square. If you don't remember, it does not matter. In any case, I can calculate the covariance. This is a matrix which is related to the interconnected variance in the system, which is the expected value of what? Of the vector ak minus, which is in a row column, excuse me, multiply the same vector but in row form, transpose. I don't know if you remember. If you transpose in a vector, you have in a row. I can do the same from the a posteriori error covariance. Now, with these two definitions, if I plug in, look, in these equations here, in particular in the first one, this expression here, which is the a priori estimation. Look at this. A minus k is uk minus ak hat minus. If I put this expression here, if I put this expression here, and then, believe me, if I try to apply, we can see here, yes, we have a minus, of course, a minus k and transpose. Believe me, if I do all calculations, I don't want to be boring. And if I apply the hypothesis of Gaussian mean value 0, believe me, I don't want really in this course to be boring. If you consider also the independence of the noise, you can, if you have interest, you can look at the slides, don't do. Believe me, at the end I have this equation. It's easy to do, use the definition. If you remember the expected value and what is the covariance matrix and so on, but it's boring. We can see here the hypothesis at the end of the mean value of expected value 0. And this is the definition of the covariance matrix of the process noise. You remember this? We did this, I told you here, very quickly, but I told you that the vector W, the system noise variable, or variables, if you like, is in a vector form, characterized by normal means Gaussian distribution with the expected value 0 and covariance Q. The covariance is defined, I recalled here. I will use this definition here during the calculations. During the calculation, believe me, we can see also here. We appear here after the products. I do the product and we can see here the a posteriori covariance matrix. Don't learn this. At the end, we have, using the hypothesis, this equation here. Of course, if the hypotheses are not guaranteed, we don't have this equation. We have another Kalman fit. Again, why Gaussian, independent, all hypotheses which I told you in this course. Let me go ahead. Equation number 3. We are running fast. And I try to implement if I have time. Look, this is the equation number 3 of the Kalman fit, in which Kalman put this equation here as a possible hypothesis. He says that the true, the approximation of the true, xk is the true. What I know plus what I don't know. The approximation of the true, better to say the approximation at the second step, the correction of the approximation of the first step, which is in the second step, is xk hat, which he says, is put as an hypothesis, equals xk hat minus what I know a priori, plus, look here, the parameters which change over time at each step, multiply, look, please pay attention, what I am measuring minus the corresponding estimated variable, corresponding means if I measure the current, the corresponding estimated current, at a priori step. Because if you remember, age characterizes what I am measuring. You remember zeta k hat equals age multiply xk hat minus. I don't know. Also here, no? I didn't put it here because here is the true, but the approximation hat is without this. It's clear what I intend. No? If I don't put this, I don't have the truth ZK. I have ZK hat because hat characterize something which is it's not the true because the true is what I know plus what I don't know. Assuming here ZK, which includes VK. Yeah, VK. No? VK is in the measurement noise. I mean, here is what I becomes from the measurements minus, yeah, let me say the ideal measurements. Excuse me, the a priori, no? Let me say exactly what is the a priori estimation. It's not the idea, the a priori estimation. This is the innovation. The innovation, the name is very important because it's the difference between the information which I have from my real system and real measurements, because both have errors characterized by W, the real system, and the real measure characterized by V. Basically, our approximation of the true, is what I know in advance, and I have to consider now the innovation between what I am measuring and what I thought, because K minus depends, is something related to the a priori. This means a priori what I think about the system, a priori knowledge. Multiply, please pay attention here, and the parameter which we will see depends on our a priori knowledge. This means our a posteriori is my a priori plus something which meets my a priori knowledge plus my experience. This multiplication is extremely important because multiplication means meet. Meet is a semiotic concept. You know semiotic. Semiotic is clear. It's the meaning of the symbols, sign of the sign, semiotic. A multiplication in math means to meet. We are close. Here we add something plus is more intuitive. We had my a priori knowledge, what I have in my mind, what could be, in my opinion, no? A priori knowledge. Something which is inside me. Immanuel Kant, you know Immanuel Kant? A priori knowledge, time and space is something which, if you don't ask me what the time is, I know what the time is, but I cannot answer what, because it's something a priori, concept a priori. I cannot explain exactly, but I can improve the concept of my a priori if I meet my experience. ZK minus H minus XK hat minus is my experience. The difference between my experience and my a priori. Innovation. If I'm able to build a difference between my experience and my a priori knowledge of the reality, I have an innovation in my knowledge. But this should meet my a priori concept. Weights by my a priori concept. We will see KK. Now, let me go ahead here, because here is for engineers. We can see a lot of calculations, which is not the goal of this course. Believe me, and let me go to the slide number 32. Just to repeating the a posteriori covariance matrix, which is defined in this form here. And let me, this is just a repetition of the definition of the a posteriori covariance matrix as the expected vector of the product between the column of the a posteriori error and the row of the a posteriori error in the matrix. Now, here's the key point. I am almost concluding. Look, in order to calculate KK, which is something which depends on my, we will see, on my a priori knowledge. When my a priori knowledge meet my experience, xk minus h multiply xk hat minus is the different my experience and my a priori knowledge. Kalman says, if I plug in now, here xk, which I already presented. If I plug in here xk hat, which I, in the matrix C, in the equation C already did as a possible solution, and then I consider the trace of pk. What is the trace of pk? In the matrix, the trace is the sum of the diagonal element. If I do the minimization of this trace pk with respect to kk, we will see some interesting results. Let me go ahead. Here, we can see here that I try to minimize the trace of pk with respect to kk. I don't know if you remember in math. Here is more complex. If you consider this in a matrix, this is in a vector, could be also in a matrix, kk. But you remember in high school, when we have a function, in a parabola, how we can find the minimum? We do the derivative, equals 0. Here, pk is in a particular matrix, which is in a definite positive matrix. Forget this. Anyway, the derivative equals 0 characterizes, minimum and maximum. But if you know that the function to be minimized as particular characteristics, for instance, it's in a convex matrix, this means if pk reflects this convexity. Also, in this case, a little bit more complicated because we don't have one variable if you have a matrix. But anyway, just to sketch the concept, if you do these calculations, I mean, I show you with the book the calculation, you don't have to learn. Here, the trace is the sum of the diagonal element. The sum of the diagonal element are squared. I don't know if you remember the definition here. This, the sum of positive elements, think about in gymnasium, in a parabola. Which we have, in any case, a minimum, if you like. But everything is dependent on k, because xk hat has this expression here, which depends on k, because it's here. It's here. It's here. If you do this boring calculation I show you in the book, at the end, believe me, it's easy, even though boring, to calculate kk, which is this one. Now I show you, you don't have to learn. This is the equation number 5. Very important, because we can see that depends on our a priori knowledge. when our a priori knowledge, this means what I cumulated through this recursivity, meet, multiply by my new experience, which is what I, let me say, perceive minus what I knew, I increase my knowledge of the system. I increase my knowledge. Philosophically, extremely important, this concept here. And this is basically the value pk at this point, at this value here. Do you remember? I minimize pk. This is the solution. For this kk, I have the minimum of pk, and this is the minimum of pk. I don't do the calculation, but we have 5 equations. Let me show you how long and boring are the calculation. Which one? These calculations. You don't have to learn. Therefore, I didn't put also here. I have here the book. But the calculations or these computational aspects are not so difficult, just boring. I think now I tell you a couple things, and if I have time, I will start with a possible simulation. Otherwise, we will start next week. Let me show you just for curiosity. Yeah, I found it. Look. Look. He called, and the notation is a little bit different, no? This a posteriori covariance matrix, J, this tilde means error, a posteriori error. No? This is the a posteriori error. The trace, you remember I told you, the sum of the diagonal elements, and then it tried to dig the, I don't know if it's visible, probably not very well. No? Better? Yeah. He called J the a posteriori covariance matrix. Trace, as I told you, the sum of the diagonal elements. Exactly what I told you, but he used J instead of P. Everything is in a function of K, P and KK. Look, I mean, I don't want to be really boring. No? You remember this? And at the end, believe me, you already. This is another form. Is another form of the same solutions which I presented, but is, believe me, is exactly the same. This is what I told you. He does the calculations in a different form, but my idea is to present the beginning this equation here, even though I present in a different form, but it's the same. And this here, which is exactly what I told you. I come back. If you put this expression here, we will obtain what I told you. Believe me. But anyway, so in 3 pages or the 4 pages of calculation, which I would like to avoid because they are quite boring. I think today I don't have time to start with the simulation. Next week, just simulations. Let me nevertheless do the last considerations. We can see that I can express kk, everything as a form, as a function. If I do the calculations, it's so boring. We will obtain kk as present in the book. You don't have to do. You can believe me, because pk minus can be written as in a form of pk. You can include here, and then you have to do the calculations. In this form here is, in my opinion, is more it's basically in the majority of the books is written in this form here. Equation B and equation D. We have now discuss a little bit these two equations, because these two equations are particularly important, because in these two equations appear Q and R appear explicitly, and Q and R characterizes our statistical aspect of the Kalman filter. Now, it could be that we can know, not always, the variance of the covariance R matrix, more or less, but this more or less is also a problem. If I have a model in the output, we cannot know exactly. We will see during the semester. In any case, Q is really difficult to be estimated. We have methods, PSO, neural networks, and so on. But Q and R typically should be calculated, should be known in order to have the solution. Of course, this cannot be known because, they are statistical form. This means we cannot, in particular Q, we cannot characterize the model using an uncertainty, a Gaussian uncertainty with Q exactly which reflect the reality. This holds also for R. This means Q and R can be used as tuning parameters, as the tuning parameters. What is the meaning of the tuning parameter? Yeah, with a different criteria, we can set suitable value of Q and R, of Q and R. And criteria could be exactly try to minimize the a posteriori PK matrix using, for instance, neural network, particle swarm optimization methods, and also different methods. What is the meaning, nevertheless, of Q and R? We can see directly from here. Very small r, characterize very small value of r. Let me consider just one measurement. R is a constant. Very small r value characterize very precise measurements because output equations, because we assume that the variance of the error in the measurements or the variance of the error in the output is very small. This means we trust the measurements. And if R is very small, trusting the measurements means KK are relatively high. We can see from this equation that I weight the innovation stronger because I trust the measurement if R is small. Vice versa, if R is large, K will be small because I don't trust the innovation. I trust more my a priori knowledge, because if R is large, this means that the sensor or the knowledge in the equation and the output they are not precise in the sense. The same consideration can be done from Q. Q very large means that our a priori knowledge, our model, is not reliable. This means I cannot trust the model. We can see from here, for very small q, we have very small k. Excuse me. Yeah, for very small q, very small k, this means when q is small, in this sense, we trust the model. No? Again, if q is large, we don't trust the model. If q is k is small, we trust the model. We can see from here that k will be, we have in the numerator this value here, will be very small. This means the approximation, now, the posterior approximation is mostly depends on my a priori knowledge, because I don't weight the new experience too much, because I trust more my a priori knowledge. Vice versa, as I told you before, also considering R very small or Q very large, I combine my a priori knowledge with my experience. There is another important aspect here in this equation here. At the beginning, if you consider k equal 1, we have A which multiply P 0. This means we have an initial value of the error, which basically should be known, but of course I cannot know, because if you remember, the initial error is here. X0, this cannot be known, because this is the true. This is what I know plus what I don't know. And this x k hat. This means also P0 could be considered as a tuning parameter. At the end, look, because do you remember I told you that here we have a minus, here we don't have minus, k minus 1 is the preview approximation. Look, I can summarize 1 minute, and then next week I promise you, we implemented the Kalman filter during the lecture. Look, we have 5 equations. We will come back a little bit also on the equation. 2 equations characterize the state prediction. Equation 1, equation 2. Very important to notice, we don't have minus here, because x hat is the a posteriori correction, but the previous step. We can see here that from the previous step, we will update for the new step. This means this element here, x hat, came from here, in particular from the equation 2. In the implementation, it will be extremely easy to understand. Here is a little bit difficult. I show you the lines in the program. But let me conclude. I need to start in a P0. Here is not well written, P0 is not there, but try to image. But it's written, it's not well written, but it's initialization of x k minus 1 and p minus 1. This means x hat 0 and p 0. It's not very well written, but initialization means x hat 0 and p 0. Of course, this I have to guess. I will come back on the simulation a little bit to understand better these 2 initial values. In particular P0, extremely important. Also, this is important. More important if the system is nonlinear, is not this case here. I'll tell you why later. This is the equation 1. We start with this equation here. We calculate this equation 2. Then we go here. We can see that I can calculate, because I have a p minus, this kk at the step k, we have in the correction phase. I will calculate xk for the next step, and I will calculate pk for the next step. Now, I put, please pay attention here, the recursion. Xk minus 1 hat equals Xk, because I re-update for the next step, the state and the error. And then I loop again. Each time I loop again. Next week, we will repeat just shortly the meaning of these equations, but in particular, we'll repeat the concept using the Kalman filter inside the MATLAB, so we can understand a little bit better these abstract concepts. As I told you at the beginning, the idea is to show you something more intuitive than considering mathematical aspects, just flesh out. And this is a little bit the meaning of this course. Then now we concentrate on the linear case of Kalman filter using MATLAB Simulink. Yeah. And then when we consolidated our knowledge, we will go ahead with the nonlinear case. No? But I try to consider some possible exercises. Okay, I stop the to record, and then we can discuss if you have questions or the thing.